Hey, what's up, you guys? Welcome to the second video in our series, Vic Explains Calc 3 Concepts. So for today's lesson, we're going to be maximizing profit using optimization. And we're going to be working on this problem right here. So let me read it for you guys. It says, a company manufactures two items which are sold in two separate markets where it has a monopoly. The quantities Q1 and Q2 demanded by consumers, and the prices P1 and P2 in dollars of each item are related by the following functions. P1 equals 600 minus 0.3 Q1, and P2 equals 500 minus 0.2 Q2. As the price for either item increases, the demand for it decreases. The company's total production cost is given by C equals 16 plus 1.2 Q1 plus 1.5 Q2 plus 0.2 Q1 Q2. To maximize total profit, determine how much of each product should be produced and find the maximum profit. All right, so all of these words right here pretty much just mean what I wrote right here in my work, right? So we just have P1 and what it's equal to. We have P2 and what it's equal to. And then we have the cost function. And then we want to determine how much of each product in order to maximize the profit, right? So we want to start off by considering the revenue formula, right? So we know that revenue is going to equal price times quantity, except in our case, we have two products. So we want to do P1 times Q1 plus P2 times Q2, right? So now that we have our revenue equation, now we want to consider the profit formula, which is going to be equal to revenue minus cost, right? So we're going to substitute in this expression right here and this expression right here in order to get our profit equation, right? So we're going to do this right here, P1 Q1 plus P2 Q2 minus the cost function, which we already have. It's going to be 16 plus 1.2 Q1 plus 1.5 Q2 plus 0.2 Q1 Q2. So the issue right now that we're having with this equation right here is that we're working with four variables, right? And that's going to be very difficult for us to solve. So instead of that, we want to substitute in this expression right here for P1 and then this expression right here for P2, right? So once we substitute that in, right, here for P1 and then here for Q2, now we're going to be left with the profit function, except only in terms of Q1 and Q2. And that's going to make it a lot easier for us to work with, right? So now that we have this, we're just going to do some simple algebraic manipulation or simplification, right? And then we're going to be left with this profit function right here, right? Okay, so now that we have our profit function in terms of two variables, now we want to start the optimization process, right? So let's just go back to our notes here real quick for a second. We have right here. So in order to find the global maxima and minima, the first step is to find the critical points, right? So since in our case, we're trying to search for the global maxima, right? That's also going to be our first step. So find the critical points of P, right? So in case you guys forgot, right, what are critical points? So go back to our 15.1 notes. We know that the critical points are going to be where the gradient vector is either the zero vector or undefined, right? So what does this mean, right? What we can do to find when the gradient is zero, right? We can just get when the x component is equal to zero and when the y component is equal to zero, right? And then we just solve for x and y. Except in our case, we're working with Q1 and Q2, right? So let's do that. So we're going to find P sub Q1, right? The partial derivative of P with respect to Q1, right? We're going to find that right here, right? We just get our function right here. Then we take the derivative with respect to Q1, right? So we get this right here, negative 0.6 Q1. Here we treat like a constant. Here we bring here. This we also bring here. And then these two we treat like constants, right? So this is our partial derivative right here. And we want to set this equal to 0, right? So once we do that, let's do the next one, right? So P sub Q2, right? Just the same process as before. We want to treat the Q1s as constants, right? And take it with respect to Q2, right? So we're left with this right here. And we want to also set this equal to 0, right? So now that we have these two equal to 0, we want to find Q1 and Q2, right? So what we can do here is let's take this left one, right? This is what we did here. And then let's just solve for Q1, right? We could have solved for Q2. I just chose to solve for Q1. So once we solve for Q1, we get Q1 in terms of Q2. So now we can substitute this into our equation right here, right? This is just simple systems of equations, right? Stuff we learned in high school. So now that we substitute this in right here, we only have one variable now, Q2. So once we do some simplification, we're eventually left with Q2 equals 896.7, right? So now we can substitute this value of Q2 into our equation for Q1, right? And then once we simplify, we're left with Q1 equals 699.1. So boom, that is our critical point right there. That is when our gradient vector is equal to 0, right? All right. So now let's go on to step 2. All right. Let's see. So for step 2, we want to investigate whether the critical points give global maxima or minima, right? So what we're going to do here is we're going to do the second derivative test. Let me also go back to that to remind you guys. So the second derivative test is when we take the second derivative with respect to x, multiply it by the second derivative with respect to y, and then subtract the partial derivative with respect to xy, and then square that, all right? So that's the formula for the second derivative test. Let's go back right here. So that's what I did. I got P sub Q1, right? It's just going to be negative 0.06, right? And then P sub Q2, that's going to be just negative 0.4, right? Everything else we treat like constants. And then P sub Q2. You just go right here, take this with respect to Q2, constant, negative 0.2, right? So now we plug these three values into our formula right here for the second derivative test, right? So once we do that, we are left with 0.2. So 0.2 is a value greater than 0. So what does that mean? So if d is greater than 0, so now we know it could be either a local max or local min, right? So now we got to look at f sub xx, or in our case, p sub Q1. So we know that that's going to be a negative value right there, less than 0. So when we go back here, if d is greater than 0 and this is less than 0, then it has a local maximum at that point, right? So let's go back. So now we know that at our critical point that we just found, the p function, the prof function, is going to have a local max. All right, so now that leaves us at step 3, which is where if the region R has a boundary, which it does, investigate whether f attains a global maximum or minimum on the boundary of R, right? So let's find this region R, this boundary, right? So in order to find the region R, we know that if we just think about a real life scenario, right? We can't have like a negative quantity of products we're selling, right? It's either going to be zero or greater than zero, right? We can't have a negative item. So we know that Q1 has to be greater than or equal to zero. And the same for Q2. That also has to be greater than or equal to zero. So this is essentially how our region R is going to kind of look like, right? But before we go any further, there is one important thing to consider, right? Our profit function is actually an elliptic paraboloid. So really, our local max is actually the global max. Let me explain real quick. So if we go back to our profit function right here, right? We just want to look at the dominant terms, right? Which are going to be the highest degree terms. So we have negative 0.3 Q1 squared, negative 0.2 Q2 squared, right? For the sake of visualizing the graph, we can kind of ignore all these other terms, right? So when looking at just these two terms, we see we have a negative squared variable and another negative squared variable. So this tells us it's going to be the elliptic paraboloid, right? It's that bowl shaped, right? And since they're both negative, that tells us that it's going to be pointing downwards or opening downwards, right? Let me just show you guys a quick visual representation of the graph, right? It's going to look something like this, right? The bowl shape just opening downwards, right? And you see here that I only use the dominant terms just for the sake of visualization, right? I know that obviously on the exam you wouldn't be able to use one of these, but this is just for you guys to get an idea of how it looks like, right? So that's pretty much it. We know that we don't have to check the boundary because we already know that the local max we found is our global max, right? So now that we know the point for the maximum, let's substitute that in to our profit function and find our maximum profit. So that's what I did here, right? We have our profit function, right? Negative 0.3 Q1 squared, and then dot, 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 a lot of other stuff, right? So when we substitute that in, right, for each of these, it's a very long expression. I just put it onto my calculator. We're going to be left with this as our maximum profit, right? And of course, I just rounded to make it easier down here. So that leaves us with our final answer. The company should produce Q1 equals 699.1 units and Q2 equals 896.7 units for a maximum profit of about $432,797. All right, guys. So that about sums up today's video. I hope you enjoyed watching. I hope you learned something from today's lesson. And that's it for today. If you have any suggestions, any critiques, let me know in the comments down below. And that's it. See you guys next time.